number 9, we're given this differential equation using this operator notation of capital D, which, I could multiply all this out and get a horrible looking differential equation, but that would be a big mistake to multiply it out, because this is what my characteristic equation is going to look like. So it's still a constant coefficient differential equation, so my characteristic equation is going to be exactly the same as what how this is factored. So it's going to be r minus 2, r minus 1, r plus 1 cubed, and r squared plus 4 squared equals 0. Since that's nice and factored, I can see my solutions. I'm going to get a 2, a 1, and a minus 1 3 times, and then this one, r squared plus 4, when I solve that, I'll set it equal to 0, and I'll get plus or minus 2i. So the solutions to that characteristic equation are 2, 1, negative 1 3 times, and plus and minus 2i. So from that I can write the solution down. The solution would be, since this only occurs once, it's some constant e to the 2x. This occurs once, so constant e to the x. And then this occurs 3 times, so I have to account for all 3 cases. I've got c3 e to the minus x, then I've got c4x e to the minus x, and then one more, c5 x squared e to the minus x. And then for the non-real, it's e to the 0 and then sine and cosine of 2x. Well, e to the 0 is 1, so I won't put it. So I'll have c5 cosine 2x and c6 sine 2x. And so that accounts for all the roots for that characteristic equation. And then the last problem here, we're going to go backwards this time. Given the solution, I've got 3 solutions to this third order differential equation. I want to create the differential equation from the solutions. Well, so like I said, we're just going backwards. From here, I can see what the roots were of the characteristic equation. So my characteristic equation had roots, because I've got e to the 2x and x e to the 2x, I know that 2 is a repeated root. And here I've got e to the 1x, so 1's also a root. So there's my 3 roots, which means that my characteristic equation had to look like this. It had to have x minus 2 in there twice, and x minus 1. Yeah, well, not x, but r. Those are r's. That's my characteristic equation, so I'll multiply this out. I'll get r squared minus 4r plus 4. I need to multiply that by r minus 1. And I need to multiply it out because I want to get it in this form here. Here, I could do the differential notation and just do d minus 2 squared, but I was asked to get it in this expanded form. So when I multiply it out, I'm going to multiply r times each of these. That'll be r cubed minus 4r squared plus 4r. And then I'm going to multiply minus 1 times each of these. It'll be minus r squared plus 4r minus 4. And then collect them. I get r cubed minus 5r squared plus 8r minus 4 equals 0. So therefore, the differential equation then is minus 5y double prime plus 8y prime minus 4 equals 0. And then I'm supposed to go ahead and check that it works for e to the 2x. Well, let's see. So y1 is e to the 2x. y1 prime is 2e to the 2x. y1 double prime is 4e to the 2x. And y1 triple prime is 8e to the 2x. So plugging that in, I've got 8e to the 2x, that's the triple prime, minus 5 times 4e to the 2x, that's y double prime, plus 8 times 2e to the 2x, that's y prime, minus, that's supposed to be over 4y, 4 times y, which is 4 times e to the 2x, that's supposed to equal 0. Well, let's check. I've got 8. There's how many e to the 2x's I'm going to have. I'm going to have 8 of them here, minus 20. I got 16 and another minus 4. That's how many e to the 2x's there are. And if all was right with the world, yep, got positive 24 and negative 24 does equal 0. So You could check all three of them, but this was easy enough to check e to the 2x that it does work out.